Hello friends, in this video we will learn the operation of DC to DC converters. So what is a DC to DC converter? As the name suggests, it takes a DC input and it produces a DC output. For example, you can feed it a 10-volt DC input and you can get a 15-volt DC output from it. Then it is a boost converter because it boosts the input voltage. In the same way, for a 10-volt input voltage, we may get 5-volt output voltage. In this case, it will be called a buck converter. And there is one more converter, that is the buck boost converter, that can produce both a high voltage or a low voltage by using the same circuitry. Now, let's see how a basic step-down chopper operates. For that, let us assume we have an input voltage of 10 volt and we have a switch. We don't know what switch it is, just for the time being assume there is a switch operating and there is a resistive load here. I want to get 5-volt voltage here. Will this circuit work? Let's find out. When the switch is off, basically there is ground. We will have, if we plot the load voltage, this is what I want. Let's plot the load voltage. When the switch is, let's say the switch is on, then I will have 10 volt across the resistive load. This is 10 volt, and for the time when the switch is off, I will have no voltage across the load, 0 volt. And again the switch is on after some time, again I will get 10 volt, and again the switch will be off, so again it will be 0 volt. So let's assume the switch is operating with a time period of t, which means this time is t, and in this time interval, for the time dt, the switch is on, and for the time 1 minus dt, the switch is off. Then what will be the average and RMS voltage in this case across the load? Let's find out. To find the average output voltage, we will use the formula average output voltage equal to total area by time period. Now what is the total area? The total area is just this shaded area, and this is a rectangle. So area is height into width, and this area is nothing but 0 plus 0, and what is the total time? That is this time, t. So we will get Vs dt over t. This t and t will cancel, so we will get d time Vs. This d is called the duty cycle or duty ratio. What is this duty ratio? It's the time for which this switch remains on in its interval. In this time interval, the switch in our circuit is on and the source is directly connected to the load. And for the rest of the time, 1 minus dt, the switch is off. Here is one more term that you have to know, that is called a mark space ratio. This is nothing but the ratio of on time and off time. So this is nothing but d is to 1 minus d. Now, as you can see, this is not a DC, not a perfect DC, because this voltage waveform has a lot of ripple. We don't want it. So how can we filter out these ripples? We can add a filter, right? So let's see what happens if we add a filter in this circuit. Now in this circuit, we have added an additional filter. This is an L filter and this is a C filter. So combinedly, this is an LC filter. What does this L filter do? This makes the load current, that is this load current, more continuous. That is, we know that inductor cannot allow sudden change in current. So this makes the load current more continuous. And this C makes this voltage, that is the load voltage or output voltage, continuous in the same way. Because we know a capacitor doesn't allow sudden change in the voltage across it. And the voltage across the capacitor is nothing but the voltage across the load. So this works as a current filter and this works as a voltage filter. Now what happens is, when this switch is closed, current starts to flow from this through the inductor, and when this switch opens, what happens to this current? Because we know this, the inductor doesn't allow the current to suddenly drop to 0, but here this current has to drop to 0. Then where will this current flow go? This will produce a large voltage across the inductor, because we know the voltage across inductor is L di dt, and suddenly you are changing this di from the load current to 0 in very small time. So this makes a high voltage VL across the inductor. this can create sparks across the switch to make the current flow. This can damage the circuit. So what do we do for this? We add another component, that is a freewheeling diode. This is called a freewheeling diode. Now when this switch closes, then the current that was flowing through this inductor, this current has a path now. It will flow through this freewheeling diode, so no voltage spike is produced. This is a standard buck converter circuit. Now we will analyze the voltage waveforms and output voltage of this circuit in detail in the next slide. Now the question arises, what is this switch? So we can use many devices for this switch. We generally prefer what's called an IGBT as a switch. We can also use a MOSFET or a BJT, but the preferred industry preference is an IGBT. An IGBT has a collector and an emitter like a BJT and a gate like a MOSFET. So it's a very good switch, and we provide a gate pulse in this IGBT to turn it on or off. In this plot, we have shown the gate pulse switching action of the IGBT. We provide the gate pulse for a duration of dt in its entire time period t, and for that time only the IGBT switch will be on. This is a control switch. So what happens at the voltage at this point, that is across this diode? When the switch is on, we see that this whole voltage is appearing across this diode. So we'll have voltage equal to the input voltage Vs across the diode. And when the switch is off, this diode will start conducting. Then this diode will basically short it like this. So we'll have zero voltage across it, and this pattern will keep repeating. So this is the voltage at this point. Note, this is not the load. The load is after the filter. So we will filter out this voltage to get the load voltage. Now let's see how the current waveform in this inductor is. Initially, let us assume the current is, some value of current is flowing, and when the switch is basically on, the current will keep rising because there is now a source in the circuit. And when the switch is off, the current will keep decreasing because now there is no source in the circuit and the inductor will lose its energy. And this waveform will keep continuing like this. We will come back to this waveform later when we will calculate the ripple in the current. Then we will be discussing in more detail. Now, what will be the output voltage waveform? For the output voltage waveform, we are basically filtering out this thing. So this output voltage waveform will also increase like this, and then slightly there may be some ripple. But what will be the value of this output? See, this capacitor will pass all the ripples in this the voltage that is appearing before the filter. So what will pass through the filter is nothing but the DC component of this waveform. The DC component will pass through the filter and appear as the output voltage. That is nothing but D times Vs. So we will get a pure DC voltage at this point, whose value is D times Vs, and we will get a ripple voltage at this point, that is like this. So I hope your doubt is cleared. What happened is, in this year's GATE exam, that is the GATE 19, there was a question asked about a DC to DC buck converter, and many students confused it with a chopper circuit. So let me discuss what happened. A chopper circuit is nothing but a circuit like this only. It only chops the input voltage waveform, like, you know, we chop something with some kind of a knife, chop some things like this only. It chops that. We have a input voltage continuous like this, and what happens is this switch chops out some part of it, and then remove this part. It chops the voltage and it keeps some part of it and removes some part of it. Then what's the voltage across this resistance? The voltage across this resistance, there are two possibilities. One is the average voltage, another is the RMS voltage. What is the average voltage? As we had seen earlier, the average voltage is nothing but D times the input voltage. But what is the RMS voltage? If we find the RMS of this waveform, please find the square of the RMS. That is nothing but energy upon time period. What is the energy of this wave? The energy is energy, that is energy of one cycle. Okay, the energy is nothing but amplitude square into duration of the wave, that is divided by time period. What is the amplitude? That is Vs. So this is Vs square into dt by t. This t will get cancelled out, so we will have RMS square equal to Vs square into d. So if we take root on both sides, the square term will get cancelled out and we will get a root over. That is the RMS voltage that is appearing across this load resistance. Note that d is less than 1 and root over d is greater than d. That is, the RMS voltage appearing across this load is more than the DC average voltage. And for a resistive load, for power calculation, we will always take the RMS voltage across the load and divide it by the resistance. That is something we know from our circuit theory knowledge. So in this problem, in this type of question, if it is a chopper, then the power delivered to load is the RMS voltage across the load square divided by the resistance. That would be, if we square up this thing, it is d into Vs square divided by R. But in GATE 2019, the question was about a DC to DC buck converter, and a buck converter by its property holds a filter in it like this, and there we can have the load and the switch, and there is also a diode for freewheeling purpose. That is the original circuit of a buck converter, where we have pure DC input and we get a pure DC output. What is this DC input? That is Vs. And what is this DC output? That is dVs. We don't have any chopping action at the output point, because this capacitor will bypass all the ripples that appear at this point. Here we have this chopping from, so we will have a voltage dVs at this point across this load. So if we calculate power now, power is nothing but, we know for resistive load we calculate as it as RMS square divided by R. But for a DC waveform like this has average equal to RMS equal to d times Vs. Because if we calculate RMS here, what is RMS? RMS is nothing but the total energy, that is amplitude, that is Vs dVs square into duration by duration. Take root of this whole thing, this dt will cancel out and we will get dVs only. That is for a square waveform. You can check in other ways also. For this type of DC waveform, we will have RMS and average same value. So we will have d square Vs square divided by R as the output load power. In the next video, we will see more about this buck converter, such as discontinuous conduction and input resistance and repair, those sort of things.